axiom of choice and continuum hypothesis. This is the question that has shaken humanity for the centuries. Part 6. 2. Cutting a sphere into pieces of larger volume. Is it possible to cut a sphere into a finite number of pieces and reassemble into a solid of twice the volume? This question has many variants and it is best answered explicitly. In two polygons of the same area, is it always possible to dissect one into a finite number of pieces which can be reassembled into a replica of the other? Section theory is extensive. In such questions one needs to specify. What is it? Piece. Polygon? Topological disk? Borel set? Lebesgue measurable set? Arbitrary? How many pieces are permitted? Finitely many? Countably? Uncountably? What motions are allowed in reassembling translations? Rotations? Orientation reversing maps? Isometries? Affine maps? Homothetas? Arbitrary continuous images? Etc. How the pieces are permitted to be glued together. The simplest notion is that they must be disjoint. If the pieces are polygons, or any piece with a nice boundary, you can permit them to be glued along their boundaries, i.e. the interiors of the pieces disjoint, and their union is the desired figure. Some dissection results. We are permitted to cut into finitely many polygons, to translate and rotate the pieces, and to glue along boundaries. Then yes, any two equal area polygons are equi-decomposable. This theorem was proven by Bolyai and Gurwin independently, and has undoubtedly been independently rediscovered many times. I would not be surprised if the Greeks knew this. The Hadwiger-Glur theorem implies that any two equal area polygons are equi-decomposable using only translations and rotations by 180 degrees. Theorem 5. Hadwiger-Glur, 1951. Two equal area polygons P, Q are equi-decomposable by translations only. IFF we have equality of these two functions, var phi underscore P equals var phi underscore Q. Here, for each direction v, i.e., each vector on the unit circle in the plane, let var phi underscore P, v, be the sum of the lengths of the edges of P which are perpendicular to v, where for such an edge, its length is positive if v is an outward normal to the edge and is negative if v is an inward edge. In dimension 3, the famous Hilbert's third problem is, if P and Q are two polyhedra of equal volume, are they equi-decomposable by means of translations and rotations, by cutting into finitely many sub-polyhedra, and gluing along boundaries? The answer is no and was proven by Dane in 1900, just a few months after the problem was posed. Über Raum gleich Polyeder, Göttinger-Necricken 1900, 345 to 354. It was the first of Hilbert's problems to be solved. The proof is non-trivial but does not use the axiom of choice. Follow my page and save this video so you don't miss the other videos that are related to the axiom of choice and continuum hypothesis. And if you are interested in